This video tutorial is going to go through the last coordinate system that we'll have to know in this course. It's called spherical coordinates. So in the past few videos, our goal was to try and represent a point P in space in different ways. So in terms of 3D space, we had Cartesian coordinates where we had the XYZ axis, and in order to reach an arbitrary point P that we drew, we had to move X units away from the origin on the x-axis, y units away from the origin in terms of the y-axis, and then z units up towards the z-axis so that we arrive at point P. So that's the Cartesian coordinate system. With the cylindrical coordinate system, you basically have, let's say, a distance r over here, and let's say this is the x-axis. So you're going to turn this r away from the x-axis, and that angle is called the azimuthal angle, phi, and then you're going to raise the tip of this radial arm z units up to point P. So with spherical coordinates, it's a little bit different. We're still trying to figure out where point P is, but we have to redefine a few things. So I've drawn this diagram. I don't have a whiteboard yet, so a sheet of paper is going to do. As you can see, instead of having R over here, we're just going to change our perspective, and we're going to label the direct distance between the origin O and P as R. So this R is no longer the radius per se, it's just the direct distance between O and P. So with this line, we can project it down towards the XY plane, and that means it's going to have a certain value over here, which was our old version of R, and we're just going to ignore this r sine theta for now, but we know that this distance over here, or this value, is going to be phi away from our x-axis. So that hasn't really changed. Phi has remained, the azimuthal angle is still there. Our r is now different and redefined, but because r is now pointing up towards P, it means that it's also going to make a new angle theta with the z-axis. So in spherical coordinates, we have three variables we have to look at. We have r, the distance between O and P. We have phi, the azimuthal angle. And then we have theta for the angle that r makes with the z-axis. And in order to calculate what this distance is, which is useful for integration purposes, and we'll cover this in a bit, we can form a right angle triangle here. And because of this right angle triangle, we know that this is going to be r sine theta. And because this is essentially a parallelogram, these two lengths are going to be equal. So if it's r sine theta up here, that means the projection of r onto the xy plane is going to be r sine theta as well. So we're going to go through all this in detail in this lecture. And remember, spherical coordinates does get a little bit complicated if you don't understand it. So if you are struggling with any part of this video, please do seek support whenever you can. Let's quickly go through an overview of what I just drew. So we're going to redraw what I just showed you from scratch, just so that we know where spherical coordinates come from. We're going to start off with our three axes, x, y, and z, with an origin over here. And we already know that we can represent point P as x, y, z, or P r phi z. So that's Cartesian and cylindrical coordinates. And with both of them, with cylindrical coordinates especially, we know that there is a projection of the of that point onto the xy plane. So that's basically the height. And so right here, and then we represented this as r. And this was phi. So now I don't want to call this r, I want to call this r. So with spherical coordinates, I'm no longer looking at r on the xy plane. I consider r to be the direct distance that point P is away from the origin. And with that, I'm able to come up with another expression for this. So let's start here. R is now at an angle of theta away from the z-axis. But because of that, and because of where r is, I can actually get the projection of r onto the z-axis, which would give me a right angle triangle. That means sine of theta is equal to opposite, where this is the opposite side, over hypotenuse r, and opposite is equal to r sine theta. But this length is the same as this length. So this is equal to r sine theta as well, and it's called the projection of r onto the xy plane. So now with spherical coordinates, we know that we can represent a point P using r, phi, and a new angle theta. So the unit vectors are going to be r hat, phi hat, and theta hat. And we can represent this on our drawing. R hat is going to be pointing radially outward, because that's the direction that r is going to be changing. When we're swinging r sine theta around on the xy plane, we're swinging it in this direction because phi is the angle that r sine theta makes with the x-axis. So this would be phi hat. And for our new angle, we want to relate r to the z-axis. So when r is at the z-axis, we start at 0 and we swing outwards. So then this swings this way, and it's called phi hat. So now we have three different unit vectors. And with three different unit vectors, it means that our values are changing in three different directions. That means I'm going to be able to figure out differential length elements for each, and then come up with differential surface elements and a differential volume element. So we're going to go through an analysis of differential elements now. So let's just go through differential elements. So this is going to be very difficult to draw, but I do have to sketch out the coordinate, the axes again. So we have this, x, y, and z. So the easiest thing for me to do is to actually draw a part of a sphere. So we'll do that in black. So if I have the part of a sphere like this, and this, and that, it's somewhat like a sphere. This is my origin, and I'm just going to take a look at r sine theta. I have in blue r sine theta, with this being phi. I know that r sine theta is going to be changing with respect to the x-axis because the direction, the unit vector for phi is in this direction. So that means I'm going to move, let's make this much bigger. So this is going to be an arc length, and it's going to be r sine theta d phi. So remember, before we had r d phi for cylindrical and polar coordinates. Now we have r sine phi d phi, r sine theta d phi, because this is the new length that we're looking at. So this would mean we've changed a tiny step of d phi, and with that, we should be able to tie it back to the top of the sphere, like so. Exactly like this. Now our point P was elevated, so if I consider this to be our, let's say our point, the center of our wedge, we know that there is r sine phi d phi over here. We also know that there can be a change in the distance r. So r is the direct, so there's a change in r like this. So this would be considered dr, with this being the original length r up to here. So if we do have that, it means that we started off with an angle theta, and this is going to be d theta. And this is a curved length, so now we have to figure out the arc length. It's going to be r d theta for this. I hope this makes sense. So kind of got to make this look a little bit more 3D. We can have this and then this, just to tie things up. Okay, so now we have this like 3D wedge that we call a differential volume element because there's three lengths that we looked at. So let me just go down here. We're going to look at our differential length elements. We know that we have dr, we know that we have r d phi, and we know that we have r sine theta d phi. This means if we wanted to calculate the differential volume element, we know that dv is equal to, so any volume is equal to length times width times height. So there are 3 length elements. We're just going to multiply them all together. dr r d theta times r sine theta d phi. So dv is equal to r squared sine theta dr d theta d phi. Okay, so if we were trying to calculate the volume of a sphere, so let's try to volume of a sphere, then we're going to have to integrate with respect to our differential volume element. So integrating dv is going to give us the volume of a sphere. But we need to figure out the boundaries, and there are 3 different variables, so that means we're going to need a triple integral. So let's take a look at the boundaries. They're going to be for r values. We have it going from 0 to capital R, the radius of the sphere. For your phi values, from our polar and cylindrical coordinates, phi is the one that you spin around a full revolution. So we have 0 to 2 pi for this. And for theta, keep in mind that if you're already spinning r sine theta around 360 degrees, that means you already have a disk. And if you're rotating a disk, you only rotate it 180 degrees so that you cover all 360 degrees on both sides. So theta, so think about it like this. X, Y, and Z. If I already have the area of a disk from my r and my phi, that means if I spin it around, I only need to spin it halfway, so from 0 to pi, in order for it to fill up an entire sphere. So here we have 0 to pi for our boundaries. And when we calculate the volume of a sphere, we have V sphere is equal to the triple integral. So we have these boundaries that we have to put in. And we have r squared sine theta dr d theta d phi from our dv. So we just put that in there. And once again, we try to see if our equation or our function inside is separable. I can separate it into r squared times sine of theta. So that means I can separate this into 3 individual integrals. So I have V sphere is equal to the integral from 0 to 2 pi of d phi times the integral from 0 to pi of sine theta d theta, and the integral from 0 to r of r squared dr. Now we have 2 pi minus 0, which is just 2 pi. The integral of sine theta is negative cosine of theta, and we're going to solve from 0 to pi. And we have the integral of r squared being r cubed over 3, and solve from 0 to r. So now we have 2 pi minus cosine of pi minus cosine of 0. So cosine of pi is going to be -1, so we have minus 1, which gives us 1. Minus gives us a plus cosine of 0, which is a 1. So we have 1 plus 1. Then we have r cubed over 3 minus 0. And I have 2 times 2, 4 pi r squared over 3. And that gives us the volume of a sphere. So we figured out volumes. Now we should probably figure out the surface area of a sphere. So with the surface area of a sphere, we're going to need to define a differential surface area element. We need ds, a differential surface area element. So I'm just going to scroll back up to our drawing. When we want the surface area, we really just want the area that's bounded by the red and green lines. So we're only just looking for everything at the top, or the outermost portion of the sphere. So we know that the red is r sine theta d phi, and we know that the green is r d theta. So that means we have ds is equal to r d theta times r sine theta d phi, and ds is equal to r squared sine theta d phi. So to calculate the surface area, we now have different boundaries. We know that the boundary of phi is going to be from 0 to 2 pi, and we know that the boundary of theta is 0 to pi, and we have r squared sine theta d phi. Similar to cylindrical coordinates, where we're trying to calculate the surface area of a cylinder, we can make an assumption about the letter r, or the variable r. If we're trying to calculate the surface area of a sphere, the assumption is that your r value is going to be at its maximum value of the radius capital R. So we can say, but r is equal to r at the surface. So SA, we can take out the r completely, so r squared, and then the integral from 0 to 2 pi, integral from 0 to pi of sine theta d phi. So is this separable once again? We have this function sine theta. That is just one variable. So yes, we can separate this into two different integrals. We have r squared, 0 to 2 pi d phi, the integral from 0 to pi of sine theta d theta. And to solve, we have r squared, 2 pi minus 0, which is just 2 pi, and the integral of sine theta is negative cosine of theta, and we want to solve from 0 to pi. So SA is going to be 2 pi capital R squared. We solved for this before. This was simply 2. So we have 2, and therefore SA is equal to 4 pi r squared, which is the surface area of a sphere. So that pretty much wraps up spherical coordinates. On a last note, between engineering and math, you'll be taking a lot of math courses in your career here at the University of Waterloo, and unfortunately, the theta and phi angles are swapped in their field. So, having taught different math courses here and also physics and engineering courses, they keep flipping them around regularly. But for this course, for E&M and ECE 106, we're going to be adhering to engineering ISO standards. So wherever I've defined theta and phi to be, that's what we're sticking with throughout the whole course. I just wanted you to be aware, what we call theta is what mathematicians would call phi, and vice versa. Although it doesn't really matter as long as you understand what is happening, this is a really common question that students ask, and it's important to note that there are different conventions used in different fields. But like I said, as long as you understand what each of the angles mean, then you're good to go.